In my review of Accurascales' excellent Mk5 coaches, I did express my disappointment at both the trailer car directional lighting and the overall coach lighting across all 5 cars. The latter was a particular frustration, so I've decided to do something about it. This video will cover a low-cost, low-effort and fully reversible modification to each of the 5 cars that should go a long way to improving this aspect of these models. Hi, thanks for joining today's review. First, I want to kick off with a few important points on this upgrade before we get into it. We'll then look at the design approach for the upgrade, and we'll follow that by looking at all of the components and tools required to complete the upgrade. We'll then get into the implementation on one of the Mk5 coaches. Following that, we'll check it out on the layout to see how it compares to the existing coach lighting. Lastly, I want to touch on the directional lighting in the trailer car, why I believe it's performing as it is for many users, and what you can potentially do to improve it. Okay, let's get into it. A word of caution before we go any further. As the implementation of a change of this nature is likely to invalidate your warranty, you need to ensure your coaches are good in every other respect before getting into this, so that any pre-existing warranty issues can be addressed. The good news is that Accurascale have already done most of the hard work for us with their existing implementation, so the upgrade is going to be nowhere near as onerous as if we were adding coach lighting from scratch. The next point is that this upgrade will be fully reversible. We won't be making any changes to what has already been implemented, and it'll be a simple task to remove the upgrade at any point in the future if you so wished. Only basic soldering skills are required to perform the upgrade, making it suitable for even relative beginners to give it a go. A consequence of all of the previous points is that the upgraded LEDs will always be on and won't be controllable via the wand. You will still be able to turn on and off the existing LEDs, but the main seating area will remain lit at all times, as this is where the new LED strip will be deployed. With the particular LED strips I have chosen, there is a difference in color temperature between these and the existing LEDs. The difference will be visible in the vestibule areas at either end of the coach, as this is where we will continue to use the existing LEDs. Personally, I'm okay with this, as I believe the LEDs I'm adding are a more correct color temperature and I can live with the difference. You can always choose an alternative LED strip with a color temperature you are more happy with, and that will better match the existing LEDs. It's up to you. If having a different color temperature in the vestibule areas is too much for you, you can always add the new LEDs to these areas as well, but it will more than double the amount of soldering you need to do, along with the extra wiring required to feed power into these areas. So let's look at a high-level circuit diagram of the existing coach lighting. Stay alive capacitor on the left is a 5.5 volt 0.22 farad capacitor. I will include a link to the datasheet in the description. A typical DCC stay alive would be 12 volts, which is why this stay alive can't be used for the directional lighting in the trailer car. On the right hand side we have the wand detection and LED drive circuitry feeding the existing 5 LEDs per coach. There's 3 LEDs in the main seating area and 1 each in each of the vestibule areas. It's the 3 LEDs in the main seating area that we will be replacing by installing the LED strip over them. Here I've overlaid the components we are adding, which for each coach would be a resistor and an LED strip with 13 LEDs, each of which has its own 100 ohm current limiting resistor fitted to the strip. As these sit in parallel with the existing LEDs, they won't impact them as already mentioned, and they can easily be removed in the future if you wish to reverse the upgrade. Resistor RL is used as a current limiting resistor for the LED strip, and varying this resistor will either increase or decrease the brightness of the LEDs on the strip we are adding. I've done a bit of experimentation, and the 2200 ohms seems to give an appropriate level of brightness using the LED strip I have chosen to go with. Increase the value of this resistor if you want to make the coach lighting a bit darker, or decrease it to make it a bit brighter. Once you go below about 1500 ohms, you may notice a flicker in the coach lighting when the coach is running. I'll talk about the reason for this in the last section, but for now you probably need to run with a value of no less than 1500 ohms for a resistor RL. If you choose to use an alternative color temperature LED strip, the value of the resistor RL may need to be adjusted. The same applies to strips other than the one I have chosen to use here. Alternative strips may have larger or smaller current limiting resistors on each LED, and this will impact the value of the resistor RL, so you may need to do your own experimentation to get a light level you are happy with. Now, as you can see from the upgraded circuit, we haven't changed anything from the original circuitry. We will be covering the center LEDs, so you won't notice whether they are on or off when the upgrade is in place. We will continue to use the outer LEDs, as I've already mentioned, which does mean a variation in color temperature versus the main seating area. You could look to cut off some additional LEDs from the strip you purchased to cover the vestibule areas and wire these into the strip in the main coach area. This will give you a uniform color temperature throughout. I was happy enough to run with the existing LEDs for these areas, so it's up to yourself if you want to do the extra work to cover these as well. Now let's look at everything we need to perform the upgrade. I'll put all of the details I'm covering here in the description so you can check that out afterwards. First of all, we need a 5V LED strip with a color temperature in the 5K to 6K range, which is typically referred to as a daylight or a cold white range. These can be purchased on Amazon for about £12. For the strips I purchased, they came in 2 reels in a box, and you'll only need less than one of these reels for this particular upgrade. You can keep the remaining reel for other lighting applications on your layout. I've put a link to these particular LEDs in the description. Next, you'll need 5 2200 ohm quarter watt resistors. A 5% tolerance level is fine for this application. You can use higher wattage resistors, though you ultimately don't want the resistors to be too large, or they may cause a fit problem when putting everything back together. Again, I'll put a link to representative resistors in the description. You'll also need a soldering iron with some solder. If you don't own one, you can pick up soldering kits on Amazon for as little as £13 for a 60 watt soldering iron. Many of the kits come with other useful tools such as cutters, soldering pump, etc. Make sure you get an iron that has different tips for the soldering iron and a holder for the iron. Again, I'll put a link in the description to a typical kit that I would recommend purchasing. You'll need some reasonably fine wire so that it's flexible enough and easy to work with. We won't be passing a lot of current to the strip, so even something like single core wire wrap wire would be fine to use. You'll also need a suitable wire cutters to cut the wire and resistor legs to the desired lengths and strip back the insulation on the wire. Most LED strips will come with an adhesive backing, but this won't stick very well over the existing LEDs that are in place. Rather than use this, I'm going to use some sellotape to hold the strip in place. You won't notice this when you look in from the outside. It will keep the strip flat in the areas over the existing LEDs in particular, and is easy to remove if you want to reverse the upgrade or change the strip in the future. It's optional, but I like to cover the resistor and its legs with a heat shrink to reduce the risk of short-circuiting anything, particularly if one of the resistor joints broke and the resistor was floating loosely in the coach. Shortening the stay-alive capacitor, for example, would not be good. You'll need a small Phillips head screwdriver to remove the 2 screws retaining the main PCB. Again, you may get this as part of a soldering kit if you go down that route. As the coaches do have a lot of underbody detail that could get knocked off during the upgrade process, it would be no harm to have some plastic glue on hand to glue back on any pieces that fall off. If you're choosing to add passengers, you can use it for those as well. For illustration purposes, we're going to be upgrading Coach D from the 5-car set. The procedure is more or less the same for each coach, but I'll talk about the differences you'll encounter as we step through the process. The first thing we need to do is get the body off. I found it easier with the coaches compared to the trailer car. Once you get it over a couple of the clips, it comes away pretty easily. Just be careful with the underbody detail. Patience is king when removing a coach body like this. Next, you want to remove the 2 screws that hold the PCB to the body of the coach. When you lift it off, you will see the 2 springs that connect the base of the coach to the PCB. On the top side of the PCB, you can see the 2 terminals from the stay-alive capacitor and the wand and LED circuitry. Underneath, we have the stay-alive capacitor itself and the 5 LEDs that illuminate this particular coach. We're going to use the two capacitor connections from the upper side of the PCB to connect in our upgrade. I had originally considered removing one of the LEDs on the underside and using the pads from it to connect in the upgrade. There are a few potential problems in doing this, however, not least of which is the physical size of these LEDs and hence the size of the pads they reside on. Removing the LED and using these pads is a job for someone with experience in working with surface mount components and who has the appropriate tools for the job. As most modelers won't be in that category, I've chosen not to go there. The next thing we need to do is measure out our LED strip and cut it from the reel that it comes in. To cover the required length for this particular coach, we'll require 13 LEDs from the strip, so we cut this off with the scissors. All of the coaches have differences, so the length and number of LEDs will vary for each coach. If you're using a different type of LED strip, then the density of LEDs could also be different. I'm taking my cut from the end of the reel, as the start of the reel has a USB connector attached, which could come in handy when I go to use the portion of the reel that's left over at the end. We'll add some solder to the two contact points we will be connecting to on the strip, as this will make it easier to solder on the wires when the time comes. For most of the coaches, we will be connecting the wires to the first plus 5 volt and ground terminals on the strip, but depending on the particular coach and how long a strip you are using, you may need to use one of the inner terminals to connect to. Make up two wires, one for the plus 5 volts, which we will connect to the resistor, and another for the negative connection. The length of each wire will need to be sufficient to wrap around the PCB edge and connect to the terminal pads you are using on the LED strip. In general, you'll need between 3 to 5 centimeters of length on these wires. The negative wire will be connecting directly to the negative terminal of the capacitor on the PCB. I'm using an orange wire for the positive here and a purple wire for negative. Red and black would be easier to follow perhaps, but this is spare wire that I have that I wanted to use up. Trim back the insulation on both ends of each wire and add some solder to each end. Now cut out the 2.2K resistor. I've trimmed the legs by about 50%. We want enough length to solder to, but not too much, as we will be using the insulated wire to wrap around the PCB to the LED strip positive terminal. Put some solder on each of the resistor legs. We're going to use some sellotape now to hold the LED strip in place on the underside of the PCB while we work on it. We won't be fully strapping it down now, as we need to test everything is okay first. It is rare, but sometimes you can find a bad LED on these strips. On the top side of the PCB, we soldered the 2.2K resistor to the positive terminal of the stay alive capacitor and soldered the negative wire, purple in this case, to the negative terminal. Solder the positive wire to the other end of the resistor. You should add the heat shrink to the resistor at this point. We need to wrap the two wires around the PCB now to align with the two pads we are using on the LED strip on the underside of the PCB. Once you have bent the wire into shape, solder the positive wire, which is orange here, to the plus 5 volt pad of the strip, and the negative wire, which is purple, to the corresponding negative pad on the LED strip. At this point, we're ready to test out our handiwork. Before doing that, we will need to screw the PCB back onto the base of the coach. Make sure the two springs are in place to provide the connectivity to the PCB before screwing in place. You may also need to adjust one or more of the wires to accommodate the configuration of the base of the coach. In doing so, just be careful not to break any of the solder joints. Now let's compare the modified coach with an existing one. The out-of-the-box lighting is patchy due to the fact that there are only 3 LEDs. The vestibule areas are actually okay, as a single LED is bright enough for those areas. On the modified coach, you can see the different color temperature and the uniformity across the passenger area of the coach. We've gone from 3 LEDs to 13 LEDs after all, so it should be a lot better. I have another modified coach here that I prepared earlier, and this shows the effect of the tinted windows on the brightness. I think the brightness level is about right, and if you look up from underneath, I think the aesthetic of the large flat LEDs looks much more like real lighting than the point lighting of the original LEDs. You also don't really notice the sellotape that is holding the strip in place. You can clearly see the difference in color temperature here now between the main seating area and the vestibule areas. I can live with it, but if it bothers you, there's the option of purchasing an LED strip with a warmer color temperature that would more match the existing LEDs. As I mentioned earlier, the LED brightness can be reduced by increasing the value of the current limiting resistor RL. Again, it's up to you if you want to do this. At this point, I'm going to complete the remaining coaches with the lighting upgrade, which should give me a level of coach lighting that is closer to what I was expecting from day one. The component cost is very modest, as is the work involved, and as mentioned before, the upgrade can easily be removed if required, with all the existing lighting still in place if you ever want to revert to it. Before I finish this video, I do want to touch on the directional lighting in the trailer car and why I believe it's as poor as it is. Let's remove one of the bogies to take a closer look as to what's underneath. This bogie is off one of the coaches, but the same bogies and connectivity mechanism are used across all of the cars, including the trailer. Here we can see the two contacts that are connected to each bogie, one to each axle. These feed into the coach via two spring-loaded contacts. This keeps the whole assembly very neat, but it does have its drawbacks. Consider the example in this diagram of the pickup configuration for a Hornby DVT, for example. In this case, there are pickups on each wheel rather than each axle, so you have twice as many pickup points. Secondly, the pickups are physically wired into the main PCB, rather than having to traverse a mechanical spring contact mechanism. Looking at the two diagrams, which do you believe is going to deliver the better lighting performance? I think it's a no-brainer, and it's borne out by the directional lighting performance on the trailer car. Without the stay-alive capacitors, the coach lighting on all 5 cars would also flicker. While the Hornby DVTs have a high level of running resistance due to their heavily sprung contacts on each wheel, the consequence of this is a good level of connectivity and a solid level of lighting stability without requiring a stay-alive. It's the same for something like the Bachmann DCC coaches. So if you want to improve the directional lighting in the trailer car, the first, simplest improvement is to ensure all of the contact points, including the 2 spring-loaded ones, are as clean as possible. Some viewers have indicated that this was sufficient to eliminate the flickering, but it didn't do it for me. Plan B requires a DCC decoder with a compatible stay-alive power pack. I mentioned earlier that reducing the current limiting resistor for the coach lighting below 1500 ohms could result in the added LED strip starting to flicker. This occurs due to the fact that the voltage on the positive rail of the stay-alive capacitor is slightly higher when the power is coming from the rails than it is when you're in stay-alive mode. The onboard WAN detection and LED drive circuitry is either compensating for this, or the lighting level is such that there is no visible difference, hence the coach lighting looks stable at all times. With the 2.2K resistor in place, this is also the case for the LED strip as well. At lower resistor values, however, the increasing brightness reaches a point where there's a notable difference between when connected to the track and when it's not, and this results in flickering as the track connectivity is intermittently lost even on clean sections of track. So in summary, the bogies on these coaches look good and provide a very neat mechanism for connecting the track power to the lighting circuits. From a manufacturing assembly perspective, this is much simpler to deal with rather than having to deal with the wiring connected to each bogie. From a connectivity performance perspective, however, these bogies aren't as good as their predecessors from other manufacturers, and you need the stay-alive capacitor to compensate. With the stay-alive in place, this will give you better lighting robustness overall, as even the likes of the Bachmann DCC coaches can experience brownouts over dirty track and point work. So that's my take on upgrading the lighting in these coaches, and a relatively simple upgrade to the existing passenger area lighting that doesn't cost a lot to implement and doesn't require any destructive changes to the coach to apply it. I'm happier to use a cooler temperature lighting, even though it does differ from the original LED color temperature. These same strips are available with a warmer color temperature, so you can go with that if you prefer. In daytime running, the lighting upgrade isn't that visible, though the sequence of LEDs on the roof does provide a more pleasing and realistic aesthetic to the original 3 LED configuration. With the lights turned down, I just feel the 5 cars have a much better look, and all they need now is some passengers to complete the job. So how do you believe the new lighting compares to the old, and would you be tempted to do the upgrade? As always, let me know in the comments. If you've done your own upgrades to either the coach lighting or the directional lighting in the trailer car, please let us know what you've done and how it has worked out for you. So thanks again for watching today's video. I look forward to seeing you on the next one. And in the meantime, take care and happy modeling.